So today we're going to start chapter 10, which is about probability. So it's my assumption that at some point in your mathematics classes you've talked a little bit about probability before, but we have some vague notion as what it is. I'm going to kind of go slow through this, but I do, expect that some of this should sound familiar. So probability is a numeric representation of how likely an event is to occur. So when we talk about probabilities, oftentimes we'll abbreviate that with P. And for an event, we'll often use like a capital letter and use like a function notation. So this would be read as like the probability of event A occurring. So all probabilities are non-negative. And in addition to that, they are all bounded between 0 and 1. So if the probability of event is 0, that implies that that event is impossible. And if the probability of an event is 1, that implies that that event is certain. And the sum of all the events or the sum of the probability of all the events possible has to come up to be 1. So, as a kind of corollary to that, we have an important property about the complements of an event. So the probability of an event not occurring is 1 minus the probability that that event does occur. And this should feel, although symbolically maybe looks a little confusing, but I think when we do an example, you're going to see that it feels very common-sensey. So if Larry Bird makes a free throw 90% of the time, what is the probability he doesn't make a free throw? So common sense would say that probability is 10%, right? Should be obvious that that's the case. That's essentially what we're saying here. So the probability of a missed free throw is 100% minus the probability of the made free throw. So that's 100% minus 90%, or the 10% that we just were certain was going to happen just by using kind of some common sense. Is everybody okay with that idea? So again, this complement property that we stated up above sounds kind of confusing and symbolically maybe looks a little confusing, but it's really just basically common sense, right? So what's the probability of something not happening? All the probability left over other than when it does happen. So that's the first section. So section 2, and this, I think section 1 was just like an introduction. Section 10.2 is about the sample space. So that's probably a new term for most of us. The sample space is the set of all possible outcomes or events. So, for an example, to just give you an idea of kind of what we mean here, say we are tossing 2 coins. The sample space is the set of outcomes for that event. So the event is tossing 2 coins. So when I toss 2 coins, what could happen? I could get heads and tails. I could get tails heads. I could get heads heads. And I could get tails tails. Everybody okay with that? So this is our sample space. The event is tossing 2 coins. And each one of these guys are outcomes of that event. Does everybody feel okay with that vocabulary? Okay. The rest of section 10.2 is going to be dedicated to different ways to represent sample spaces. So one way to do that is just to write it as a set, like we did up here. Another is a grid diagram. So an example of a situation where it might be useful to do that. Let's say we roll 2 standard 6-sided dice. And we want to look at the sum. So one way to do that is I can make like a little X and Y axis, where the X-axis I'll say represents the first die and the Y-axis represents the second die. So what are the possible outcomes from the first die? I could roll a 1, a 2, a 3, a 4, a 5, or a 6. How about for the second die? Well, I could roll a 1, a 2, a 3, a 4, a 5, or a 6. Everybody agree with that? Now, the combinations of them are all also possible. For example, I could roll a 1 on the first die and a 1 on the second die. I could have a 1 on the first die, a 2 on the second die. I could have a 1 on the first die, 3 on the second die. Does everybody kind of see what we're doing here? So we're just plotting a point that corresponds to each possible outcome. So where are the points going to be on here? Every lattice, right? Everywhere where one of these two numbers kind of intersects. So how many possible outcomes do I have then? 36, right? Why 36? Well, it's a 6 by 6 lattice, right? Now you might say, why in God's name would you arrange your data that way? It seems like that's not very useful. Well, here's what's useful about it, is if I look at, say, this diagonal here, what can I say about all the sums on that diagonal? Well, for this point, I have a 5 and a 1, so the sum is 6. Here I have a 4 and a 2, so the sum is. Here I have a 3 and a 3, so the sum is a 2 and a 4. And a, oops, did I circle the wrong thing? I think I did. Beep. Yeah, I did. Okay, sorry guys. When you circle the wrong things, it's a problem. So here's the 4 and the 2. Here's the 5 and the 1. Jeepers creepers. Good thing it's easy to erase here. So there we go. So if I wanted to say the probability that the sum is 6, what would I say that probability is? It can happen 5 times out of a possible 36. Okay with that? So is it necessary to draw a grid diagram? No, it just is sometimes a convenient way of organizing a sample space. Let's look at some other ways. A very important one is a tree diagram. And in my experience looking at previous IB exams, between parts 1 and parts 2, almost always will I see a probability question involves either filling out or having to make or completing a tree diagram. So this is a very, I think, common way of representing a probability in the IB world. They seem to like these sorts of things. So let's give an example. Say that we have a bag of 10 marbles. Say 3 are green and 7 are red. Two marbles are drawn in succession. Not really sure how to spell that word. With replacement. What What do I mean by replacement? Is I'm going to draw one marble, look at what it is, put it back in the bag, mix it up, and then we'll draw the second marble. Everybody okay with that idea? Okay. So what we can do is we'll draw a little tree diagram. So I'll start with like a node. And then here is where the first part of my event occurs. So I'll say this is draw 1 is happening here. The possible outcomes from draw 1, well, I could get a green marble or I could get a red marble. Everybody agree with that? The probability of getting the green marble is, well, there's 3 greens out of 10 possible, so it's 3 out of 10. And I write that probability just on the line there that's going. What's the probability of drawing a red marble? 7 out of 10. So I'll write that probability on the way to the red marble. Then we'll make our second draw. So again, this over here will be draw 2. What are the possible outcomes on the second draw? I could get a green marble, or I could get a red marble. And we know the probability of drawing a green is 3 out of 10 still. And it's still 3 out of 10 because that green marble I took out, I put back in and mixed the bag back up, right? So that with replacement was an important part or important phrase there. So then I can go and fill in the rest of these probabilities. And this is the example of a tree diagram. And we'll talk about how we can use that to calculate the probability of, say, drawing a red and a green or something. Or 2 reds or 2 greens. But we're not quite there yet. We'll talk about that a little bit later. Sydney? I'm sorry, what? If I'm drawing the same thing. Well, it may not necessarily always be that way. So I just picked a simple example to kind of give you a feel for like what we mean by a tree diagram. But you're going to see that when we actually look at probabilities of independent or dependent events or conditional probabilities later, that these tree diagrams become really kind of helpful. But it's a little bit later before we're ready to do that. So I think we're on 4, right? So if we just take a student randomly selected from a class, and maybe we say, what is the probability they are a boy and play a sport? So if we consider, say, our class, in this class we have 2 types of students, right? We have boys We have girls. And then we care about whether we sport or we don't sport, right? So how many total boys do we have in this class? 1, 2, 3, 4, 5, 6, 7 is what I count. Did I miss anybody? Let me count one more time. 1, 2, 3, 4, 5, 6, 7. Do I have 9? Is that what you said? Okay. Too many heads down, I guess. And how many girls then do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Does that sound right to you guys? I'm not counting Isabel, who's absent right now. Okay. And boys, how many of you participate in at least one sport? So 8 out of the 9, it looks like. Am I correct on that, or all 9 of you? All 9? 8? Okay. And then Goyles, how many of you participate in at least one sport? Do we have 8 out of 9 again? Or I'm sorry, let's do it the other way. How many don't participate in a sport? We'll do that. That's easier. 2. So you could make like a two-way table like this. So if I wanted to find the probability that we've selected a boy that plays sports, you would say, well, there are 8 boys that play sports out of a total of 22 students, so you have 8 out of 22. This sort of situation has a special name. This is called combined events. And that happens, or we have to be careful, because it's possible to be a boy that also plays a sport, that those two events could overlap. They could happen at the same time. As opposed to something like flipping a coin, where you can't get heads and tails at the same time. Those events are called mutually exclusive. As opposed to like a boy who plays sports. Those events are combined events, because they could be overlapping, even if they may not, like we were very close to having a class where all the boys played sports. Is everybody okay with that idea of a two-way table? So again, what is it really doing? It's just a convenient way to kind of organize our counting. I think we're on 5 now, is that right? So say we selecting a musician from an orchestra, the probability that they are in the brass section, for all you musicians out there. So your pie chart will look like a circle. That's pretty good. I'm impressed with myself. And then maybe you have like wedge for the string sections, and then like a brass section. Maybe like percussion is less of those. Maybe like you got, I want to separate out the drummers from the percussion. Like maybe you got one dude that plays the harp, and we're calling that not a string, and maybe the rest of them are winds or something. And then, like, if you're given no frequencies inside of this, you would have to do this geometrically. You'd have to figure out, like, the area of the sector to do the probability. But oftentimes, in my experience, like, you'd be given a frequency inside of this. H for that one dude that plays the harp. It's an angelic instrument, though. Because angels play harps. Unless you're watching Talladega Nights and then you have an angel backup band playing like electric guitars and stuff. But that's pretty good too. So the probability then of selecting a musician who plays the brass instrument is 11 out of the total. How do I find the total? Add them all up. So let's see, that's 19, 30, 1, 4, 5, 50. So 11 out of 50. Could I draw a pie chart for combined events? No, right? This has to be single events only. And the last one is probably the second most common one, along with the tree diagram in terms of things I've seen on, or test questions I've seen on old IB exams. And that's a Venn diagram. And you guys already know what these look like. We spent a lot of time talking about Venn diagrams. But these are good for combined events also. So I'm not going to do an example where I draw a Venn diagram because we've seen lots of examples of those already, right? You would have to calculate an area and do it as a geometric probability. It's unlikely you'd see that on an IB exam. Yeah. It's more, in my experience, you'd be given a frequency in that sort of situation. Okay. That's that section. So we've been calculating probabilities here in some of our examples without actually giving you the formula yet, because intuitively most of us know the formula for a probability. So if I want the probability that A occurs, how have we been calculating that? We've counted the number of times A occurs and divide it by the total number of outcomes. Or, if you like to get fancy about it, we can do it using our set notation parlances and say, remember when we put this little n in front of a set, that means the cardinality or number of times or number of things in that set. And the U here is just our universal set. So it's just the universal set is the sample space, basically. So let's just do a couple of quick examples for something like this. So let's say the numbers 1 to 10 are written on the cards. Let's say identical cards. And placed in a bag. And you're going to draw out a single card. What's the probability of drawing a prime number? Well, that's going to be the number of primes in the interval 1 to 10 divided by the cardinality of that set, which is just 10 total, right? There's 10 numbers from 1 to 10. How many primes are there from 1 to 10? What are the primes? 2, 3, 5, 7. So we'd say the probability is 4 out of 10, or 2/5. How about the probability that we pick the number 0? What is that going to be? That's going to be 0. It's the number of zeros in the interval from 1 to 10 over 10. Well, there's 0 zeros in there, so we know that's 0. It's impossible for that to happen because it's not one of our options. You could think about it that way as well. What about the probability that we pick a number from 1 to 10? What's that going to be? It's good. So it's going to be 10 out of 10 or just 1 or 100%, right? Because there are 10 numbers from 1 to 10, and that's the total number of numbers. What about the probability that we don't pick a prime? So I used, notice there the symbol I used is that complement symbol from when we talked about set notations, or set theory when we talked about Venn diagrams and such. How would I do this? So you could do this two separate ways. You could count the number of non-primes and divide it by 10. The non-primes are 1, 4, 6, 8, 9, and 10. To give you 6 out of 10. Or the way I would prefer to do it is I would think about this as 1 minus the probability of drawing a prime using our complement rule from before. And we already solved the probability of drawing a prime was 4/10. And that lets me avoid having to do any counting. Because you imagine if we had, instead of the numbers 1 to 10, 1 to a million, it's a lot crummier situation to try to count up all the non-primes between 1 and a million. Yeah! I'm not interested in doing that. The next thing I want to talk about is theoretical versus experimental probabilities. So rather than defining these specifically, I am going to just kind of give an example. Let's say we are tossing a coin. The theoretical probability of it coming up heads is, what do you guys think? Yeah, it's 1/2, right? Half the time it should come up heads, or 50%, or 1/2, or 0.5. Any of those is perfectly reasonable. To get the experimental, what I would do is I would take a coin, and I would say I got heads the first time. So let's say we do 10 tosses. We have heads. Got heads again. That time that's a tail. It's a weird quarter with like, it's one of the state quarters, so it's, that's a problem. Good thing I got to back up. That's another tail. That's another tail. That's a head. That's another head. That's another head. How many have I done there? 8. 2 more. This is taking forever. That's another head. And that's another head. So here we'd say that the experimental probability of getting heads is 7 out of 10. Is there a relationship between experimental probabilities and the theoretical probability? There is. It's called the law of large numbers. And basically what this says is that as the number of trials in your experiment increases, the experimental probability approaches the theoretical probability. That's assuming you have a fair experiment. So I don't want to say equals. We want to say approaches. So let's say that we have the situation we were just talking about before. So what we have is the y-axis is your probability of getting heads. Your theoretical probability here is 1/2. And this blue line I'm going to draw is the experimental, where the x-axis is the number of trials. So you might see something like this, but kind of as you go, the bigger you get, kind of the closer and closer and closer you should be coming to, or the error range between your experimental and your theoretical should kind of be decreasing. So an example of why we care that this is a fair so this needs to be a fair experiment. So if you say, for example, we talk about birth rates of boys and girls, the theoretical probability of having a boy is 50%, you'd think, right? They're equally likely. It turns out empirically that's not really the case, that boys are slightly more likely than girls are. So I think it's like 51 and change versus like 48 and change. So like boys are slightly more likely to be born. Whether there's a biologic reason to that or if it's more of a socioeconomic reason, I'm not really sure, but I know that in practice, like birth rates are something where the experimental probability is different than the theoretical, and it's probably because it's an unfair experiment. So that's like a little aside. Okay. And that's on to section 10.4. So we talked about a little bit about mutually exclusive events before. Kind of the example is tossing a coin is a mutually exclusive event because you have the two outcomes, heads and tails, and it's impossible for you to get an outcome that's both heads and tails at the same time. Another example might be finishing position in a race. That's a mutually exclusive event. It's impossible to say get first place and also get second place in the same race. That can't happen. But there are things that are not mutually exclusive events. So a common one might be like drawing a student or picking a student out of a class. It's certainly possible if you're looking at the probability of picking a boy and then a probability of picking someone with brown hair, that those are not mutually exclusive. There are several boys in the class that have brown hair. So our definition for mutually exclusive is going to be probability based. So we'd say that P of A plus P of B equals P of A or B. And the probability of the intersection of P and B is 0 if and only if A and B are mutually exclusive events. And this is the same thing as saying that the intersection of these two events is empty. To use, again, our set notation language that we used in Chapter 8. Saying the probability of the intersection is 0 is the same thing as saying that the intersection is empty, because there's nothing in it. Everybody okay with that? Let's look at an example of doing this kind of a question. Okay, let's say that we have a bowl that contains 5 apples, 6 oranges, 2 tomatoes, 3 pears, and that's 11, 16, 4 bananas. And I want to say, find the probability of picking an apple. What would that be? Well, how many apples are there? How many total things are there? 20. So that's 1/4. Notice that this was just a single event, so I didn't have to worry about whether this was mutually exclusive or not. What if I wanted the probability of apple or banana? That's not spelled right. How do you spell banana? They're just all single letters, right? None of them are double. Okay, what's the probability of drawing an apple or a banana? What do we have to be careful here? Because of the or, we have to be careful. Are apples and bananas mutually exclusive? Yes. Can you be both an apple and a banana? No, right? So this is mutually exclusive. So the probability is just going to be the probability of picking an apple plus the probability of picking a banana. So that's 1/4 for the apple, and the probability of banana is 4 out of 20. So that's 9 out of 20. What if we want to talk about the probability of picking a red item or a tomato? Are these mutually exclusive? No. Why not? A tomato could also be red, correct? Are all tomatoes red? No, right? Hopefully you've been to the supermarket and seen that there's like green tomatoes and yellow tomatoes and like purple tomatoes and weird things. But they certainly are not mutually exclusive. So the question becomes, how do I deal with that? That's the subject of section 510. So in general, if we have an or probability, we can always use this formula. So the probability of A or B is equal to the probability of A plus the probability of B minus the probability of their intersection. So if they're mutually exclusive, does this formula still work? Yes. Why does it still work? Because if they're mutually exclusive, what is the probability of the intersection? 0, in which case it just reverts back to the probability of A plus the probability of B, right? And this is just the formula that we saw way, whoa, too far, back here.
Wait, what's it say down there? It's A, B. It's A, B, A. What's that mean?
Mutually exclusive.
Oh.
So I'm just pointing out to you that this new formula works for mutually exclusive events still, but will now also work for these overlapping events. Let's just stop here and we'll pick up with independent events next time.